What exactly is a matrix? Some say it's just a box of numbers, a collection of vectors, mathematical object, linear transformation, a function. Perhaps no one knows the answer. But we do know how to multiply a matrix and a vector. For example, multiplying this matrix with vector 1, 2. What we get is a vector 5, 2. And it turns out there is actually a natural way to visualize this. Firstly, we represent a vector as a physical arrow sitting in a two-dimensional space. And as the vector gets multiplied by the matrix, the tip of the arrow moves from the coordinate 1, 2 to the coordinate 5, 2. So that was a visualization for one vector. How about we try to do this with more vectors? Once again, we can represent the vectors as 6 physical arrows and observe their movements as they get multiplied by the matrix. But the original goal is to visualize a matrix, so we should think what happens to all vectors as every one of them gets multiplied. Our computer tries its best to add many arrows on the screen to create the illusion of every vector and the multiplication. Well, that was a visualization of matrix I asked for, but it's just a horrible visualization. There are too many vectors moving at the same time, too much information for my tiny brain to process, and we need to improve this. So, to improve the quality, we're going to apply 2 tricks. Firstly, let's squint our eyes and focus on a smaller region of vectors. The second trick we do is to represent a vector as a dot instead. Consider our old friend vector 1, 2. Now it's a dot sitting over there. The matrix multiplication would move this dot to the coordinate 5, 2. And we can replace all the vectors within our focus region with many dots instead. And then we observe the matrix multiplication. This is much better. We have essentially built an engine which creates a visualization for any 2x2 matrix. The very natural thing to do next is to just plug in a bunch of different matrices in there and watch the transformation of the dots on the screen. And very soon, interesting patterns start to emerge. The goal for the next part of the video is to illustrate the famous matrices whose transformation are so visually geometrical that we can even use English to describe them. And welcome to the Matrix Got Talent show. The first matrix on stage is the identity matrix, which is a square matrix that has 1s on the diagonal and 0s everywhere else. So, tell me about your transformation on vectors. Wait, there was no transformation? Nothing at all? Huh, that's kind of boring start. But this actually makes sense. If you multiply any vector with the identity matrix, you get the same vector back. So there will be no movements of the dots at all. If we try to label every matrix with a tag, what would be the tag for identity matrix? Well, I say it would be no transformation, or does nothing, boring. The next one is a scalar matrix. The numbers on the diagonal line are the same, and 0s everywhere else. So it's not saying that there is only one matrix that is the scalar matrix, but any matrix that satisfies this form is regarded as a scalar matrix. Let's try this matrix here. Wow, that was pretty cool. Our rectangle got bigger. And the notable thing is, there wasn't any sense of distortion, but rather like every single dot moved uniformly. Let's try one more. Oh, this one seems to be moving our dots even more aggressively outwards. So zoom in now. And we still see the contour of the rectangle, and the ratio of width versus height still remains the same. How about when the numbers on the diagonal line is less than 1? we see our dots moving inwards, and the border of the dots still forms a rectangle. It seems this kind of matrix has ability to scale things uniformly. For k greater than 1, the matrix is stretching all the vectors outwards. For k less than 1, the vectors are stretched inwards. For k equal to 1, nothing moves because this is the identity matrix. What interesting thing can we do about this? If you really ponder upon the idea of a shape on 2D space, then it's really just an infinite number of dots sitting closely together. And guess what? If matrix can move dots, the matrix can transform shape. And here, we apply the scalar matrix to the triangle. To take this idea one step further, a picture is basically a bunch of pixels, or colored dots. Then we can transform picture as well. Let's apply a scalar matrix to the Mario here. Oh, question. 3 dimension? That is a good question. A vector in R3 can be represented as 3-dimensional arrow, or likewise 3-dimensional dot. And if you ponder on this again, a 3-dimensional object is just like an infinite number of dots sitting very close together, which means we can use the 3x3 scalar matrix to transform 3-dimensional objects. The next one is not famous enough to have its own name. But the idea is you take the identity matrix and modify exactly one number on the diagonal line. And let's call this the of1 matrix. Dots were moving along the y-axis, while the x-coordinate is unchanged. How about a different one? Dots are moving along the x-axis, while the y-coordinate is unchanged. If we keep playing with the visual engine we have, the pattern starts to become clear. For whichever entry on the diagonal line that is not 1, but k, it scales everything along the axis by a factor of k, while the other axis is not changed. And this really has to do with our way of representing vector as dot. We let the first entry be x, and the second entry be y. Of1 matrix behaves very predictably in 3 dimension. It's the scaling of just the x-axis, just the y-axis, or just the z-axis. Hey, you back? Do you want to get scale along the y-axis? Oh, you got a question. Negative entries. We did forget to talk about that. Let's take a look at the simplest case first. When you change one or more number on the diagonal to be -1 for the identity matrix. Seems there's a reflection by the y-axis, and nothing is scaled out of proportion. This one? A reflection by the x-axis. So, why is this matrix producing some form of reflection behavior? What's the intuition here? Let's use the y reflection matrix as an example. If we consider the matrix vector multiplication, we first know that the magnitude of vector did not change, so nothing is scaled, but the sign of the first entry is flipped. Visually, this means arrows from the first quadrant move to the second quadrant, and dots from the third quadrant move to the fourth quadrant. And the exact logic of reasoning also holds for the x reflection matrix, in which the sign of the y coordinate is being flipped. But What about when both entries are negative? Is it a reflection by the x and y axis? And you will be exactly right. The sign of both the x and y coordinates are flipped. Dots from every quadrant would be going to the opposite quadrant. And this translates to a reflection around the origin. And as always, it's cool to let matrix transform images. In 3 dimension, there is one more entry that can be flipped, the z-coordinate. We will not go into the details of different cases here, but the overall spirit of reflection still holds. Next, enters the diagonal matrix, which is another square matrix that can have any numbers on the diagonal line, but zeros everywhere else. And the understanding of this matrix actually ties closely to the reflection matrix and off-one matrix we visualized earlier. Before me presenting you with the visualization, we can even try to guess what it might look like. But firstly, allow me to say something very important. Matrix to matrix multiplication is really not multiplication at all. When someone say, I want to multiply matrix B and A to get matrix C. Okay, what that person really saying is, I just want one matrix, which is matrix C, which can compose the overall transformation if first apply A and then B, but in just one transformation. For example, we can multiply or compose these two off-one matrices on the left to get the diagonal matrix on the right. And we already know exactly what kind of visual transformation those two matrices would have, since we have labeled them earlier. So what do you think the diagonal matrix would do? Exactly like what you guessed. The vectors all move along the y-axis by a factor of 2, and also along the x-axis by a factor of 3. How about this diagonal matrix here? You can pause the video and show it's just a composition of the 3 matrices on the right, which we know a lot about already. And therefore, we can conclude that the diagonal matrix must be the overall transformation of sequentially applying the 3 matrices on the right. Let's use this image as an example. Firstly, we scale the x-axis by 2.5. Secondly, the y-axis by 0.6. And thirdly, a reflection. And this diagonal matrix, which is a composition of the 3 matrices on the right, which just encapsulates the 3 transformations, but in one go. Whenever there's a diagonal matrix, you can always decompose it into a sequence of the off-one matrix, in case you have negative numbers on the diagonal. You can also explicitly factor it out to include a reflection matrix at the end. For this 3x3 diagonal matrix, we know it will just be a composition of 3 different off-one matrices, and we can directly read the numbers from its diagonal line. So it will scale the x-axis by 3, y-axis by 2, and z by 0.5. The next one is a zero matrix, which is square and everything is 0. So regardless of which vector you multiply with the zero matrix, it becomes the zero vector. And visually, it would mean no matter where the vector starts, it would move towards and end up in the origin.